Yes. Okay.
Oh, you totally.
Yes, Soji.
You're not ruled out, like.
Find it again. I can't. I need time. I need time. Yeah, it. I think so. Yeah. I think we can go back. Okay. I'll be there then. And homework 18. The 18 is going to be. What did you say? Analytical homework 18, chapter 18. Are you doing that today too? Yeah. Great. Yes. Okay. Yeah. Thursday. It's 19. That's practice. Yeah. It was 15. Or is 15 due? Yeah, yesterday. I forgot to turn mine. Yeah, he didn't mention that's why I didn't have to. I don't think he cares. Hey, how are you doing? Good, how are you? Excellent. I'm celebrating. Thank you for voting for the projects. Well, I was so nervous for about a month about the outcome of this votes that I should find better investment of the time, which I should prepare for projects rather than worry about your time. How many meetings do we have before? How many labs do we have total remaining? Next week.
Including this one?
Including this one. 3.
Including 3. If we have one dead week, then yeah, 3.
Okay, 3. And the one on the dead week will be maybe just for finalizing your video. So projects should be done on the next web in 2 weeks. So now I provide all preparation things and probably will interact one-to-one and with helpers and you during the next 2 weekends. So it's presently whatever you like, but it is recommended to consider investing time slowly but surely for the now in next lab, which is in 2 weeks. So we do have about 2 subjects which very common and reasonable for everyone independent of what you have selected. So well, maybe more, but two necessary things. One is to look at the demonstration and have a hands-on version of code that works and gives reasonable results for chemical reaction for mass substantially bigger than mass of a reactor and doesn't give garbage. Yeah, that's okay. Anyway. And such an example has been sent as an email. So as a task minimum, we all run the code and look on what it generates. Another thing that likely will be too much for today, I know, maybe I'll try, is to get hands-on onto Marcus theory on the coupled electronic and nuclear degrees of freedom. The last 10 minutes of today's meeting or send materials for and then try to maybe make it like first 10 minutes or in 2 weeks. It's better to do now because some of you are not doing it. So that you all would agree with reactant product reaction coordinate, and then one can chop the space in 2 areas. Before middle point left, right, or reactant area product. So in case you have zero L, then taking the wave function absolute value squared from 0 to L of 2 will be probability of reactant, and sometimes in the code it is referred to as probability at the left side of the simulation cell, and the part to the right from the level to say the probability of the product over time, and sometimes it is referred to as probability at the right side of the simulation cell. So in case some of you have selected projects related to chemical reactions, and then the evaluation of this probabilities simultaneously is main form of the output. So we may want to discuss the project, the media research, as converting input into output and analyzing it. So as an input, we do have the potential, we do have initial momentum, and we have initial wave function, right? And as output, as a raw output, we will have just P reactant and P product as function of time. Those are not not so simple to analyze. One may want to further process and refine and analyze this data. How do you characterize a chemical reaction? What if someone tells you by phone, I am running an interesting reaction? What are you asking your partner? Or if you have a course on synthesis, like if there is a certain reaction, what is the parameters of reaction for end user?
That's how many products, which solvent is done in.
Okay, those are more like input. And if you want to tell about how efficient the reaction, how like thermodynamic. So like delta G. Okay, activation energy. Do you know many reactions that are 100% done? So what is the percentage of the? Yes. So yield, activation energy, and if reaction goes too quick, you probably call it explosion. If it goes too slow, you just become unhappy. So activation energy, yield, and rate, right? So we need to convert the this data into activation energy, rate. Reactions in wet chemistry lab for your like educational labs or for research. Do you do you do like synthesis, purification, characterization? Do you do it once? How many times did you repeat the same reaction?
A lot of times.
But it's like 1, 10, 100,000.
We do a lot of like batches of 3 right now.
Okay,
It's like 3 reactions or 3 analyte, like we have it's like samples and analyze each one.
okay, that is great. And what is do you repeat likely in these 3 batches you repeat you try to reproduce all parameters of reaction completely identical, right? But if reaction goes too slow, what do you do?
Increase temperature
Yes.
or pressure or decrease product.
Yes, whatever you were studying as chemist, like Le Chatelier, equilibrium, stuff like this, right? How do we project it here? Being needed, huh? Yes, exactly, more momentum. So we are going to reproduce or repeat this situation for a range of values of momentum that will correspond to different temperatures, and probably we will have this probabilities of reacting the product over time, temperature dependent. So the question is, how are we going to convert it into yield, activation energy, and rate? Right? What is P reactant plus P product? 100%, yes. Can we analyze probability of reactant and probability of product at time equals infinity, or as long as is accessible for our simulation? Huh?
See what happens.
Yes. So how would you what do you think about probability of reactant development at time?
Equilibrium probability?
Huh?
Equilibrium probability?
Yes, or would you agree to call it yield of reaction?
Yeah.
Okay, so you've got yield, right? So this, for product, it will be yield. What about rate?
The average rate of change over time, so probably just a certain time. So probability of reactant of at a certain time minus probability of reactant of another time over the time duration. Just take an average.
Are we going to upload? Okay, yes. So, can I erase this little stuff? Yeah. So input, output, and analysis. So what James has suggested, we take probability of product at time plus delta t, probability of product at time t divided by delta t, right? And call it rate, and maybe perform some sort of averaging. Right? So based on the derivative, differential probability. But I'm absolutely agreeing and that James is recognizing the weakness of this approach because he immediately creates a safety cushion. He tells, take a derivative and then make an average over the trajectory. Because who knows, maybe it is fluctuations. Maybe it is not very steady, right? There should be something that is, we will try it and we'll see that this way of defining the rate will have substantial error bar.
You could, also, you could integrate and then divide by time duration as well. That's about the average of that.
Yes, if the change of concentration of a product grows linearly, then it is an ideal definition. But which orders of reaction did you hear about? Zeroth order, first order,
Second, first, second.
what is the difference between them?
Zero, it doesn't change at all with so zero order doesn't change at all with respect to time. I believe first order is natural log. And second order is reciprocal with respect to another reciprocal. So reciprocal changes linearly.
Is it about concentration of product or rate?
Product.
So not changing at all.
Zeroth order.
Oh,
Zeroth order.
next,
Log, natural log.
and next.
Reciprocal, linear.
Okay. So
Reciprocal, linear, right here.
if we have preliminary considerations to guess a certain order of reaction, we can expect that concentration of product will follow the designed functional dependence, and we just need to set parameters. Okay. So I am going with the simplest example, and probably in this labs and class and projects we will not deviate unless you do your own initiative. So, suppose the concentration of reactant product change over time as product. The reactant goes as then the product goes as 1 minus. And you find natural processes that follow this change of the concentration over time. I can give an examples. If we have, if you do not change number of compounds, if they transform, but total number of compounds stays the same, it is this one. For reactions that look like look more in a physical way, if you look for conversion of excited state into ground over time, they always go in exponential. And let's assume at the beginning that we have this dependence of reactant product over time as simplest approximation. We'll discuss what to do, how to extract the rate, and then if you need to modify this approach to more complicated orders of reaction, you can do it. So suppose we know that this is the expected dependence of the concentration of product over time. So we have numerical data. The question is how to extract the rate. And we collect numerical data and heating. If I want to feed numerical data into decaying exponential, right? Which software are you going to use? Huh?
Like a calculator, statistical
Okay,
calculator.
statistical calculator, or you have this tool in Excel, or some of you like Origin, right? What suddenly we do not have? We have only pen and paper data. It is an extreme situation that probably you'd never have in real life, but what is the principle? How do we feed the data points into the form? Especially, huh?
Rate of change is equal to some constant times the amount of reactant there, and then solve the differential equation.
Okay. So if you take derivative of exponential, we will get exponential itself is times rate, right? So one way is to take derivative of what was already prompted by James, right? What else can we do with exponential to without changing it? Calculus operations, differentiate and okay. Let's do a little experiment. Integrate of E minus K T from 0 to infinity. P here, divide by P is there, right? As a new variable. And then it will be from 0 to infinity E minus U TU 1 over K. over E subtract E minus infinity. 1, 0. Yes, no. Doubts? We have a sign for doubts. Okay, so 1 over k equals to integral, then k is 1 divided by integral from 0 to infinity or probability of reactant over time dt. Well, there are limits of applicability. This equation is perfect in case the concentration goes exponential. If it is different dependence, one need to update it, right? So suppose our code does generate dependence of concentration over time, and we can extract the yield as the probability at the final time, infinity. We can extract the rate, right? With no,
Sorry, no, like,
we can,
yeah.
we can
No.
do differential integral rate, and if it is higher order of fraction, we just continue developing methods. But there are ways to extract rate out of the concentration dependence over time. Okay, now what else we are missing? The delta G activation energy. So what do we do? How can we get it?
That's the initial momentum. See how the rate changes.
Yes, but absolutely correct. But I do need a number, and here is so it is a little game. So we already know what is the activation energy. We can subtract, we can find the top point and subtract this energies, right? So it's too childish to ask what is activation energy. But let's suppose that, like, we are not going to practice it in real, but suppose we split the class on 2 teams. One team does have a potential at a code and sits in the dark room. And another part of team doesn't see what are their potential and what are their code. So we who do not see it, we can only tell them, rerun it with different potential and give us the rate, give us the trajectory. So it mimics the effort in experimental lab when you do not, if you work with unknown reaction, you don't have computational data, you do not have characterization, you just find something interesting. You can characterize the product, but you do not know how, by which path and which activation engine goes, right? So how to find the value of activation energy? How to get this number? Is there a way to find this? I'm not including it into the didactic part of the lecture because it's a little too simple and too childish.
Energy difference of the reaction, see how much heat it produces, and find the difference with calorimetry or something like that.
It's good. But now you are already, I'm happy to hear this comment, but now you're thinking as a theorist, as a graduate of physical chemistry class or as a future participant of computational chemistry class. But if we are in a wet lab, if we, there is a mixture of solvent, there is, if we have hard time to measure the change of temperature when the reaction ends, if the overall concentration of reactant product is very dilute. If you have only the concentration as function of time and maybe rates, but we are allowed to modify initial temperature. So how can we find the activation barrier?
The slow step of the mechanism.
Hmm?
Slow step of the mechanism.
What is it?
The rate determining step of the mechanism.
Okay. If you know the mechanism, you can look at it. But is there a mechanical procedure? Like if you have only the rates measured at different temperatures. Let me give a hint. You probably will be angry at me because when you recognize that you all knew. So if the temperature, which is measured of kinetic energy, was small, was below the barrier, the rate of reaction is very slow, close to zero. As far, let's call it just energy activation. So if KT is less than the activation, then the rate of reaction goes to zero. When AT is bigger than activation energy, then rate of reaction goes to maximum, right? So we just compare the redo measurements of the reaction rate at different temperatures. And we see when there is an inflection point. So we need to extract dependence of the reaction rate over temperature. And we will have it low, 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 and then high, 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 high. Right? And the value of temperature, when it changes, it will be activation energy. Yes? So, if objects in real world have only classical nature, then this figure can be really sharp. Nothing, everything, everything. But as soon as our little atoms, molecules, electrons, and protons have quantum nature, they may tunnel, right? The reaction can go even with energies a little less than there. And there are some additional effects that make this dependence not so discrete but continuous. And here is the question: how to extract activation energy? Sounds to me that I recognize the voice. How to extract the value of activation energy out of this data? So let me reformulate the question. I know that running codes is probably much more fun, but we are covering what is encoded in the code and maybe not reviewed. I think we benefit just from discussing. So how does you may think it is ridiculous, but how does reaction rate depend on temperature? If you once again forget everything we discussed before, how does rate of reaction depends on temperature? which equation, which concept, which main developer of this concept you would recognize. Yes, okay. More.
So adding temperature basically just increases the whole kinetic energy of the system, so it'll shift it in favor of the reactive products more. Reactants or
Good. So
decreasing energy.
if I want to write a rate as function of temperature, what would be the function?
Exponential.
That's a flow. You deserve a vote as well. Just write down, maybe give the name, and tell us a little bit more. Go ahead, just don't bring it with me. We need a cheat sheet to write exponential. Perfect.
So it's the Arrhenius equation.
Yes, Arrhenius equation. Did you hear about it before?
Yeah.
Okay.
Slightly.
I haven't heard about it.
Huh?
That's been forever since I've seen that.
Yeah, because it is so simple. You probably saw it in the first week of freshman or whatever. I never can write the Swedish name. It's like combine, and then and in between it is a combination of R and H in random combination.
RRH.
Well, I am predominantly wrong by that.
So
Okay. So if we do know Arrhenius law, if we believe in Arrhenius law, and now we do the same thing. Suppose we do have a numerical data, right? So it's the higher temperatures, the quicker the reaction. Suppose we have the numerical data. How do we extract it? We can, instead of R, can again KBT. Right? If you do have numerical values of this rate at different temperature, and we need to extract value of activation energy. So how do we perform numerical fitting without statistical calculator?
natural log,
Yes,
make it linear.
yes. Natural log A over A equals E minus A over KT. And then we do ln. Then natural log of rate as function of temperature over A, mu T minus E A over KT. Right? Make sense?
Yep.
Yeah. And then if you need activation energy, you multiply everything by KT here, and you have activation energy, right? Yeah. That's it, right? So you just record the values of the rate. Take couple of points for you write instead of K, you put ln of A on the y-axis, and what would you put on the x-axis? You have seen this trick before. It is considered so simple that it is not included in any serious courses. Let me cancel this little operation and tell that. So the log of the reaction rate is proportional to inverse temperature, right? And the activation energy is the slope of this dependence. Right? So if you put 1 over temperature or 1 over Boltzmann on x-axis, log of the rate on the y-axis, then for typical reactions, it will be just a linear function, and then you need to find a slope. And the slope will give you activation energy. Right? Yeah. 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 Okay. I think it is the most important message of the whole course. The rest are technical details. You're ready to go to independent projects. Oh, well, I'm not stepping out of the room and telling you around the room. We'll continue together, but this is the main message. So the plan of the research projects is that you'll get potentials either by designing them or by borrowing them from papers. Then we redo calculations with different values of momentum. At each value of momentum, we compute probability of product as reactant product as function of time, extract rate, and then put this rate in the dependence on inverse temperature and extract activation energy. And then tell, maybe compare it with what you see by your own eyes. It is more than sufficient for the glorious completion, of course. Then you put a little explanation of the context, which reaction you are interested, why it is important, how society benefits from knowing activation energy. Go ahead, Alex. What to do with it. Okay. Any questions on this core idea? Everyone is fine with it? Okay. Some of you may be interested in the simpler the better. Some of you may want more realistic. Some of you may look into more than one dimensions, but this idea is quite universal. Right? Even in multidimensional reactions, you can identify probability of product, and you can identify how it changes over time and feed it into the study. And there are exceptions from Arrhenius law, but it's too much. Let's believe in it until the end of the course. Or if you find something deviates, you can report it as a discovery in terms of the course. Okay. So we are going to practice a little bit of this thing, just to have hands-on. And the only thing that is missing from this general material for everyone is coupled electronic to nuclear degrees of freedom. I feel energetic enough to deliver it now, but I probably it will be too much. Let's just digest this part and have a little practice. And maybe after this little practice of the code that I sent, I will just do little one-to-one interviews about individual projects. Okay? Yeah. But if you can fair, you can just demonstrate what is completed. We need to rerun it from scratch. You're done. Okay, the script that I did send 2 files, the script and the input data, right? So you need to have both the script and the input data in the same directory for them to work properly. This input data are generated by a helper, and for your individual projects, it can be redone for basically any reaction at a reasonably short time. So let's probably just run the script and see what happens. Please go ahead and make sure it works at your site.
It's my.
So you see a couple of lines. The green line is the potential. This reaction is one little part of the multi-step combustion reaction when the proton is being transferred from fuel to oxidizer. If you're curious, I can speak very long about this actual data. Lunar mission, Apollo, whatever number, they needed to safely depart from the moon. Right? When we do have cars, we ignite by the battery, right? But if the battery is dead, very old cars can be started just by rolling it downhill. But for new car with too much electronics, it will not work. And if it is a extra out of Earth's mission, you do not want to put lives under danger of dead battery. So there is a trick for the space travel, and there is no oxygen, right? So when one carries the fuel and oxidizer in tanks, and for this specific situation, they are designed in such way that they ignite as soon as they touch. So they pyrophoric, right? And the reason for this self-ignition is that as soon as they touch, the protons tunnel over a barrier from reactant to fuel, and it immediately gives an excess of energy that heats up the mixture and then goes in avalanche reaction. Oh, it's just a little story behind. It's already done. So the green line is the potential energy of that reaction. And I told just a abridged version of the story because we all need to do different projects. If anyone is curious, I can speak for these details. And here is the wave packet with non-zero initial momentum toward the barrier. Here is the energy, which is below the energy of the barrier. But as time goes by, part of the packet reflects back, one part passes through. So we measure probability. What is the portion of the wave packet that did pass through? And then we plot this probabilities as function of time. So before the wave packet approached the barrier, there is no change. And as it starts tunneling, there is a change of the product probability and decline of the reactant probability. So those are the P reactant and P product over time, right? And by redoing this calculation over and over again with different momentum, one will have slower or quicker reaction that can be fit into the Arrhenius law and to extract the activation energy. You have seen this type of images, right? Before, and you see that it's the barrier, and one part is reflected, another part is passed through. So it's more like probability distribution stuff. Questions? So everything is clear, right? So did everyone was able to get to this series of figures? Okay. So if you have selected something that has like ab initio or I promised the helpers, it means you just together write an email to the helper who will provide this data file with potential. It's not part of this course to generate it. If you select something without ab initio help, it means we will just design potential by mathematical functions, which is also doing. This paradigm doesn't immediately embrace all details of the project that you have selected, but we have time and to talk one-to-one. There are solutions and hints for each project. Do not worry. It's just one of the things that is equivalently useful and understandable, independent of what you selected for. Okay, let's maybe quickly move through the code. So loading this part, then one designs the and sets up initial wave packet, initial momentum, initial position, and there should be a piece of code that does set up the initial wave packet. So it is the same as we did before, right? So you don't see any surprises. You set position, momentum, and Gaussian wave function, and there is a width parameter. What is? Let's double check the mass. So since in this example it is a proton, so it is about 2,000 times bigger than an electron in atomic units. The scale of the changes of the position are different than for electronic motion. So for this protonic motion, one uses a little smaller scales and a little denser grid points. Otherwise, one could get a lot of errors. Okay. Replication of the same approach. This line 241 is adding together all probability, integrating probability to the central point for left, and then from the central point to the end of the simulation cell. So this little code corresponds to probability of reactant, probability of the product. They are computed at each step of the time evolution. And some of you may think on the background, why do we waste time in doing evolution of the ring? Why don't we find eigenstates and practice third way of predicting future by expanding initial condition over eigenstates? over the basis of eigenstates. In case the reactant and product are bound states, this would be quite reasonable. But you see in this example, we do have like free space. We have unbound reactant, unbound product. If you have only a barrier, it means there will be infinite number of eigenstates. So the summation of our eigenstates will be not the most efficient. So this evolution operator approach is not always the quickest, but it is most universal. Okay. So here we do accumulate the probability of reactant and product. And if we go back into the command line, yes. So average probability left, average probability right. It is dependence. So it is probability of concentration of reactant and product. And if we explore their summation, it will be constant because it doesn't go away, it's normalized to one. Now I'm looking for this expression. So paste it. So this is 1 over integration of the reactant probability over time. So this little line of code is equivalent to this one. The difference is that you see that there is a yield of reaction on the top. So difference between final probability and initial probability to have it normalized to 1. If the yield of reaction is less than 100%, then to fit it into exponential, we need to make sure that we integrate a function that does change between 0 and 1. And if we normalize it to the yield, then it will be from 0 and 1. So this is the rate of the reaction. So if I need to do project based on this potential, I would rerun the code with different momentum and tabulate the rate of the reaction. The rest can be done without this MATLAB tool. I can convert momentum into kinetic energy, just momentum squared over 2m. And then the rate, if I have many data points, I can put the rates into this Arrhenius dependence. And then for this specific calculation that was done here, the result that activation energy based on Arrhenius is about 70% of the height of the barrier. So it reflects the fact that the proton can tunnel under the barrier. And it is, well, this stuff was published. It was accepted into the journal. This if you identify reasonable subject, get potential, see that all potentially competitive. Questions about this stuff? So if we all would coherently just explore this problem, each of you could do and extract this data, right? Yes, yes. Okay. Yeah. So now please keep playing with the codes, and I will just stop by individual and chat a little bit. Right? About your individual projects, prompt the names of the helpers. So I have, well, there are, I wouldn't say reliable and reliable. All graduate students are reliable, but there are two who have time and who are ready to help, and there is a postdoc, Dr. Han, who can help. And those of you who need initial data can get help from them. That they can quote their confirmation that they are enthusiastic and they just wait a request. Oh, I took interview from Garrett what he's interested in, just composed them. Well, this is not the stuff that you probably need functional groups. Yeah. But with and without this mu group in the middle, it will have dramatically different properties. That program. Huh? What is that program? Oh, Avogadro. Just it's a free online. You install it and draw molecules. Right. Yes, that's sick. It will be well. This will be the first week of the CHEM364 next semester, and then we'll go further and further to model basically everything one can do in wet lab without making your hands wet. You good enough. I could have done it.
I'm not sorry.
Very good. Okay, thank you. So I'm very happy to see you interested in these resources. Are you just
Yeah, because you don't know how to do it.
yeah, because you know.
As someone more.
Anything else after that, dude?
Why? So can we work?
Oh, you're a chin jock.
Wow. I have looked at that. I wish. I wish.
How come I doesn't look like it is? Look like what? If I just go to his left up and cut off it. Take a screenshot. No, just pull it up. Garrett, it's kind of obvious how to use it. Whoa, how to do that?
Very low. A very fine material, which is very standard silicon, and there is an alternative to silicon and organic conductor. So you say why and one needs to separate charge. So if one of the observers
think it just means that I'm a happier person. I smile first. I'm so happy to see you because I care about you.
Structure to
And I would want to be in love with you.
Road.
I want to run away with you. I want to see this through. Good. You could say you could just go to the entrance to this team was there. It's a good thing that you can tease y'all. You heard that stuff for this generation. Another way you want something you can just trade the brand. You see this it says here it's much of a but even they have been trying to individuals into probably should have said that into the microphone.
What document are you illegally downloading?
This document. So does. Give it to me. What? Give me the document.
It's illegal.
I can't download it. Otherwise, you just need to which time because it was everyone says we are to drive back there. It's way over 700.
What document it does?
Where, Garrett?
What are you downloading? Because it might be searched by university.
Where does this?
NDSU.
Oh, I didn't know that was a search. I'm gonna get a instruction stored by Hipka. Used to. Okay. Plus. Okay, so like here, so on here now, suspension, Xavier, baked, so on. Yes. It's a little focus. Then the whole high school course I instructed to bring this. That were falls. But during the don't even with me right now. Supposed raspberry juice on a service.
Downloaded something for
Glass, just beam it out glass, and they download cover for it. That's
For my project, yeah. Okay, I was about to say, should I?
I didn't think she.
Oh,
How to download? You just. You know how to download?
Do I have it?
No, do you know how to download?
We put, I don't know what I want to download. I'm just wondering if it's something that we all.
No, this is specific to the laser power put it with semiconducting. And you see the voltage. So stop instead of not done. I'm not done. I'm not done.
Pressure.
I'm not done, Garrett. Yes, produce, which is that we're going public. Helps to. This is us, guys. Separate.
Just take a picture of that real quick.
The camera can see it already. Just wait.
Saving this as a sec.
It doesn't. Easy.
Oh, okay.
Oh, what is that program? Did you just get it already?
It's always.
I already had it.
What is it called?
Avogadro.
Is it that many gigabytes?
I don't know.
When
I just already had it.
it is the same idea, but different. Not crystalline, but they are flexible, amorphous. Interface. Or maybe Adobe Warner's editor. So perfect. No, I can feel you pushing down. Stop. Karen, you slipping again. So this. First, you run it and then you tell if you're happy with it, or you want to be a little more innovative and which is I do right now. Stop resisting.
Chemical markup language?
I
I don't know what it could,
Not going to be added to this. I'm not telling you whether like this light resistant one can. And here is all business. There is a chain. And they already have the engines that say cells. Here is red and white. The Represents.
That's not normal.
Look at the paper right there. Slows down this church.
Where's the rest of your hands? My red boy.
One dimension is exhibitions. That's right. Maps.
My skin is red.
Starting point is just to practice and see, maybe.
I didn't, don't say that.
Carol, how red your hands are, just my red hands.
Look at the blue right there. I don't believe you. What? You're so silly. Stop. Oh my gosh. Trashing so.
Whoa. Whoa.
You calm down. Hey, you know what you're doing? What are you doing?
What? What you say?
What?
Thank you for selecting. So fine.
But do you know what you're doing?
Yes. So what did he say?
Did he send you stuff?
He's going to.
What did he say?
Kind of interest.
That's the anyway. Some sort of. You selected. Well, it was the local. It's a solution. Two dimensional. That's just very same 7 years ago. With titanium oxide.
Us. We use conjugated fibers, so whether that's doped.
Okay.
I was a just remember to lab day.
Interesting. How high school is. Like crushed up cranberry juice. Between metallized glass, metallic glass. And oxide. So is that pepper juice? First paid materials. You selected. Metal centers. Area.
He said that I could go more in depth, but he's gonna send me a presentation that if I just go and kind of change time, good.
That's so sick, so why station. There are ways to. There you did it, look at you.
I just listened to what you sent me.
Oh,
I forgot to do that. No.
This one.
Oh,
All right.
Jewel.
Why
Jewel.
can't we get Jimmy Jones?
No, we can't.
What's
It
the?
depends on what the dining center.
But there's dinosaurs.
Oh, I forget about that whole place.
Those are.
John Jimmy John's is. For me.
For me, dining centers too.
Yeah, because you already paid for it.
So that's. They have beef hamburgers on a bun.
Okay.
Garden veggie burger on a bun.
They do
Or Western version.
Western burgers. In ring barbecue sauce,
They have-
bacon, cheese.
They also have onion straws.
Two dimensional. We're going. We're going. We're going. So.
Did that on me?
What?
Did that on me?
It closes at 7:30. The best time to go is at 7.
I have a little heart.
What does that mean?
So that's so.
How does Jake react to that picture?
He said, ice.
He was like, okay,
I don't really care.
So what's the thing about deal with this molecule, especially to you at that, oh.
How long are we gonna be here? Like, do I need another drink?
You need at least. Anal's gonna take an hour at max.
Which a lot of it.
Patients sort of. I don't care.
Don't look right now.
I'm looking.
I'm looking.
There is another person, London Johnson. He's 17 major, but he's sitting in chemistry, and he was doing this project 6 years ago as an undergrad. Seemed very relevant, so you might consult and request potentials and database from him if you want. Sorry for interrupting.
If I wanna put functional groups on this in ChemDraw, how would I export it?
Can I touch it?
Yeah,
Well, you can save in PDB or some reasonable format and then try to open it.
would that be?
Save as.
Save as.
Oh,
okay. And then-
You try it on your own, and also you can draw things here, which could be more clear, but here and okay, just. So, carbon, and then try, but let me just run the.
Whoa.
And if you can add. stuff. So what's we. Kind of thought. This.
I'm going to win.
No, so.
I call it dub and not jug. That's what I call it, dub. Give up President Taft vibes. He's the one that got stuck in the bed. Okay, fuck it.
Funny.
It is not one pose. Status.
You've moved your eyebrows. I believe it in my very fiber of my skeleton.
Yeah, the issue.
You have bad wire management in your body. You should take it out. Bad wire management. I told you what it means and you're not accepting what it means. I don't know what to tell you in a second. I'm gonna lay it out plain and simple. You roll a range game. This way. We get Sonic. And we go skating together. Yes or no? You're just scared. I'm gonna take you out. Let me show you. You pop out on the top. You did not just do that to me. I said I wanted to get a pic with you and you're not the one.
Here's a report over. It was like last week.
It was me.
Don't tell Adam.
We'll
I told you I had to pick up someone with rhinovirus.
Sounds about right.
I don't like Adam for that.
I like him in general.
What's wrong with that?
He kind of
He's scared of
sucks.
germs.
Sucks. All the. What is that? You use never should have used. Can you explain what that is? I wanna be random. Okay. Garrett. Uncle, that's not our relation. It's lover, Garrett is busy.
Garrett's busy, right?
Yep. It's not uncle, it's lover, Garrett. Please, Garrett, don't do this to me right now. What are you doing right now?
Garrett, I have a question. Well, you know how I make Avogadro read from a specific folder or write to a specific folder, like how I. Can I specify if I want to get molecules from my documents folder, how can I do that? So it's kind of like.
I think you just import it and then choose the folder, right? And then.
Okay, so.
I don't know how to do that. Oh, yes.
Looking for where that's my.
That was like.
So. Like a journalist and you're just mad about it. So then I was just gonna.
I was.
I said that in the microphone. Think about that. It's like, Adam's gonna be listening to this. He's gonna be like. Emma Gullus has.
It's all just a lie.
They don't know.
Do see him.
Live above us. I would not put those on. I'm sorry. You know, when people like.
Do you see that?
Oh, wow. Wow,
Yeah.
every single one had.
Well, this doesn't have.
Why is it so small? I mean, it's like perfect size. Actually. Wow. I would say so. Yeah, I prefer a smaller head.
This thing is only 100 megabytes. This is sick.
It is kind of neat. It can optimize this structure.
Yeah.
Me.
What?
It's all the GeoGebra here.
Away your finger, but maybe.
Oh my God. That's reserved for not in peak time. Just what are those layers? You can give me.
No, I just wanted to go to the right carpet.
Yeah, if I close it, think it just doesn't shut down. I have to commit to queue myself.
That it was funny.
I was feeling, Judas was a bunch. He betrayed Jesus a bunch.
Did you just say?
Said bunch. That's what I said. What are you talking about? Why are you so mean to me? That's the way. So focus.
Yeah, I'm like you.
Take your neck. And twist it.
Twist
Twist it like sometimes now. They're reaching out. What James?
This is me.
Will look bad. Say no, you look hunky as well. Yeah, you never kiss me anymore. That's the worst part. Just a month ago, it felt like lightning. But now it feels dark.
You guys could.
No, we're not. It avoids our problems with his word. Never see him anymore.
Entertainment for people in the future watch the
Versus the kids.
Don't see the kids anymore, they miss you. They confuse the mailman for dad.
What is wrong?
I miss you, Garrett. Oh, I guess he's
Look at this, like, stretching,
You're in a simulation, Garrett. It's time to come out.
it's moving.
Why is it moving? That is so laggy.
What do you mean?
Hey.
And us.
Hey. Oh, God. Like, Abba Poopa. Did we already download avocado? Perhaps. Steve, I like wasn't asking you, so that's like the problem here. Do you get it? I did it now. Make me so excited. Thanks.
How are you? Not bad. Oh, man, this is the one you could. Yeah, so you remember that? Yeah. So that's good. Sucks for you.
That's bad.
Oh, when are you gonna learn?
What?
I just sounded. I don't think
He's getting weird.
It's so good. Clearer than like other ones.
Yeah.
Go high.
Like,
Such a
Steve Irwin Day today. I wanted you to know that, Garrett.
I haven't even tried. I don't even care. I just fumbled my way through.
I can't download on like this one. I guess search up online.
Yeah, they just get it right.
It's like, I don't know about all that.
I don't.
How's it?
Yeah, yeah, I haven't liked the big one yet, but. One is.
Garrett, you got me going, Sam. I'm making it on.
Oh,
my goodness. Code away.
It's like 90%. I'm happy about. Yeah.
Just straws.
You know, good sure at it.
Yeah, that's, I think he drops one of those. But I missed the first one, or the second. So I didn't. You're dropping. Dropped with. Yeah, quit. Which I'm okay with.
That's not a boingy boingy, you know?
Including the society. Garrett. Look at me. Look at me, Garrett.
This all work.
Okay, what are you doing if I pull up on you like this?
Yes.
What's your number?
911.
Did I inquire?
I want to do things I can't do here.
9 of each, so one more of each.
That's gonna be.
That's fine by me. I know a place.
Wait, was it the
Memorial Union.
Gender neutral bathroom?
Yes.
Yeah, well, we get gender neutral.
He got you.
Is that the only thing? You say that. Then you just gonna feel real positive afterwards, though.
What are you looking kind of cute right now?
Just like you, boo.
Look at this, look at this cutie.
I get a piece. She's all yours. Well, you're all mine. Oh.
I'm sure I gotta.
He's just like, oh.
I'm sure I gotta tell you guys' names on that. What's up? I said I gotta tell you guys' name on that.
Wow, I'm scared.
Gary, you try to escape to the bathroom. I need a little assistance.
You guys will be back in 40
Just
seconds. It's fine.
No, keep texting wild. You would be surprised. 37 minutes is the shortest I've ever.
40 seconds, that will be actual fun.
It'll be all from me changes. The lead up, the actual process, and the cleanup. But another. Real hungry. Feeling real sophisticated right now. Camera's on. Makes it more fun.
Some professor's gonna come to you guys be like.
No.
You may not be in my class, but I'm still giving you an A, but you should be.
Yeah, he knows all about that. Here,
You not like the constant eye contact?
So, sorry from across the way.
But it rhymes so beautiful. Window cutting. Good. You gotta hit him with the how you, what you gotta hit him with the what's cooking good looking.
No, don't hit me with that.
Explain like what they got.
It's shaking.
It's not sending me.
I know it's shaking.
I guess.
You know where I love this.
Oh, come on, you're gonna go close to me. James is gonna show.
Like a soap opera. Listen, right? This is what I got, bro. I'll post it to the internet and I'll start making money. You guys go ahead. I'll post it to, okay.
So,
Oh.
10 minutes, we can discuss.
I'm so frightened.
Where you go, Gary Bears? When you coming back? Come back anytime soon? No. Why?
Oh.
No, I mean, I'm gonna pay still later. Don't Garrett, I miss you. This feels so empty.
My heart.
names. No, he's just so. That way he enters the room is just magical.
For the thorns, full of pain.
Honestly, it takes my breath away.
When is the Twilight monologue?
We entered a Twilight fanfic.
But there's no blue filter.
You know, Garrett's real name is like
CGI.
Barry the Darkness Triple Vampire.
Honestly, think about it.
What is the emo name?
Garrett.
We need Garrett with an emo last name.
Thank you.
Let's see what you have for me.
I don't see where your, is it 3 or 4?
I think it's 4.
Well, you can give
With my chair? No, it would be weird to me if I go over
It's like our plan.
there. Here, take my chair. I want to go catch this one.
No, I'm like, sure, like.
You look very comfortable.
Locked in. How have you feeling?
Interesting. This is so real. Oh, why, you know what's up? I'll send one back. Get ready. Wyatt, do you see what I sent you? What is that? It's me. I need that emoji. I sent him this. Oh, bet you would wanna know, right? But you left me with the kids. Childhood work. I am. Trust me. Wait, can I be the voice lawyer? Wanna make some of that? Who's that? Levi. You're a bit early, Levi. I'll represent you. I think go drop to your documents for you. You will? I'll be swearing in. Wow, I want to get my hands on some of that one. You won't do it for free? That type of free. I can work with it. Free with extra steps if you will. I'm good with that. What? Eric. Please come back.
I promise I won't sway you with my charismatic efforts. Garrett, I promise. Please take me back. Not the same anymore. Garrett, just these. Cry. My viper. These word dances.
It's time to think about what you did. How you're going to fix it.
Eric, how do we be?
He did not. Williams, go ahead.
Excellent.
Well, when was your training? So I didn't sort.
Well, in the organic chemistry, I remember seeing alkenes get reduced on a platinum surface. So yeah, that's why I selected it, because I thought that's pretty cool. But platinum reducers wasn't there. So
There it is. So, more or less. It was quite I don't think so. It was the, I don't usually did, but we did this. Okay.
it's the one part, it's like one dimension is the inter. Instance. I thought, so we're making molecular hydrogen, or we're making atomic hydrogen or molecular hydrogen with this reduction.
But probably have to take a look at this. Sorry, crossing all of them.
I did it like 40 times.
Oh,
Did you get a lot of notifications?
no, I got it once.
Damn it. I was sitting here like,
Don't expect me to follow you back though.
okay.
Take it.
So this is the anode. Is there a platinum cathode too? Or is there a different metal cathode?
You don't care about this. Would be too much.
On your Instagram.
We have it on a flow inside the electrolyte to balance the charge.
Yes.
Okay.
I think you're doing something.
Oh, but we can do this. Focus on the back of my hand. Your
We are forming, are we forming molecular hydrogen? Yes, atomic hydrogen.
all of these people. So this. Uh-oh. Well, it's shattered into the world, so it's shattered into a million pieces. Oh, no, sure. Right home. Yes. It's okay. Yes.
Showed me the other day. They're in Arizona right now.
Okay.
I can change that.
Whether in.
One breaker.
Okay.
We had any that.
So. Army man.
Matt?
We should ask him what his favorite temperature to sleep at is. It's a great conversation
What
starter.
firmness of your pillow do you prefer?
And what types of pillow, like combinations like feather? And that's if we add temperature after the fact or after the.
place, but I mean, it's something like that, that's the actual interest. One is. Charged. I don't know how the vote's gonna start. Next distance. That means the period.
It's okay. Okay, so for the reaction, we apply a voltage and then we apply a temperature. Or can we just not have the temperature apply?
Everything's gonna be all right. First part, we'll just provide the reaction. Yeah, that.
So assume that's, so the rate determining step of the reaction is the molecular hydrogen and heat combine. Tell them that's the slow part.
Dang.
Where's my whole plan for winter break?
Platinum.
What was your plan for winter break?
You're gonna hit up.
Catalyzes the molecular hydrogen.
The stuff after the biochem final.
Yes,
Why not? Still.
we assume that happens. We just write that off negligibly.
Well, we heard what I would just say is this.
I'm
simulation. Use on contrast like listen. Oh, look, same thing.
Doesn't even, I wanted to spend.
I'm sorry, I guess. You know, just because you feel like you're at rock bottom, doesn't mean it is rock bottom. You can still go.
Yeah,
It's a false spot.
Yes. You can bring through. It's like glass. Just like mine. It's like what?
just like mine.
Marriage.
Actually, in place.
So what his name is? You want or not? Okay. Are you on or is you on with an O?
W U.
Let's see
You-
what I can optimize this geometry.
Okay. One O.
Let's do gradient descent.
All right, and I'm assuming, so to start, before we inject the electrons,
Doing math.
That's the optimization.
right,
Because of gradient descent.
I'm assuming it goes like this,
Together.
the distance, it generates a negative potential. Like a negative potential, or potential goes down farther this way.
We would mention changing displacement. I just assume this is gonna continuous junction between. I need to talk to Karen.
Well, is this right before the potentials are right?
It is right.
Because, so this is the y potential before, the exponential never changes. I'm assuming but the y potential, it goes from this, or, I mean, maybe it could be.
I need to.
Assuming it's probably inverse square, so. Like,
You're in so good.
the thing goes down.
It's so good.
We are going to get this. Thank you.
You're welcome.
Right, try. Charged potential. Just setting.
Yeah, but the y, does the y, so if we hold x constant, does y behave like a line, or does it behave like a,
No.
like that? I'm assuming, or something like that.
Okay, why is a distribution to pronounce it?
Yeah.
It would be more like.
Or 1 of our squared, you mean, or something like that?
Yes.
All right, because because they're charged, so it
Yes.
just behaves like.
Exactly, yes. Weirdo.
Should I call Adam?
Do what? Ask him about the diamond.
Constant.
Times.
Two. Something like that, and that corresponds.
Mhm.
I don't know what the name of the cool constant is.
Do you know anything about the dimer?
If one does.
So how's it interacting when it's dimerized?
Just one. Okay, it just disappears.
It's
Coordinating?
This cool constant is just the same thing as 1/4 pi epsilon naught, right?
Yes.
Right. So we can just have.
The muoxo, yeah.
Makes sense.
I really want Olivia's. But I don't have Olivia's.
Several items.
Yeah.
I would find that periodic table that was.
No, we're still in.
Oh, good stuff.
I'm just trying to
Just
get more information. Make sure council talks to me.
What type of crystal does platinum form? Actually, I can find that out if I just.
And
I
Sugi,
didn't, please look at my private.
we could do it, Sugi. I'll ask. Yeah,
Something like this, I suppose.
I'll call you if that's what we do.
That makes sense.
anything like.
I mean, we might, the choices are either dining center or Jimmy John's. I think it's dining center, but I don't know.
I'll draw out something like that.
We'll have to go in two groups.
Try this sort of like.
Sugi's like,
This one?
No.
All right. I
know.
don't know what you're talking about.
Oh, okay.
Something to do it too.
Instagram
or Snapchat?
Oh, that's super. No, on Snapchat.
There ain't nothing,
This one is.
but
I'm like, you are gaslighting.
yeah, if you could send me Olivia's. I'm allowed to look at that, right? Am I? You can just forward me the email. Hold on. Yeah.
Oh, I found it now.
Kidding.
Just click what I sent.
It's great.
Porphyrin 9.
This.
Very porphyrin 9. That's heme. Yeah. No, that is heme. That is heme B. Very. Oh, it's coproheme, yeah, yeah. Yeah. Oh.
Good, how are you?
Excellent, thank you.
I was asking everyone else, how do you came to this project? Yes, yes. So just bigger ambitions.
I stacked timer. I can ask.
Right, there for some things.
That sounds like orbitals. The manuscript or Kent's paper?
And then you reach. As we did those first things.
Got it. Do you still have Olivia's?
This weekend.
Got it, got it. Okay.
So.
Okay, but then we're also. I might also look at the Miyamato. Because. Yeah, correct, because was Gudrun in there when she was talking about that? Were you in there? She said that she hasn't seen anything on that, right? So we don't know if that actually forms.
Yes.
Right? Yeah. I mean, we would assume it does, but
Church.
but clearly we know it doesn't work. That's rapid.
This I understand.
Maybe through temperature changes. I don't know how I would research that. I can talk to- I might just do the CHDC catalysis. That one also interesting. The radical mechanism.
Means average position. As we go through iterative cycle, we update evolution function, and we update the CHEM364. And each time they will go closer and closer, they will try to. And the spiral catch and the electron instead of being distributed, it will come closer. I know based on just a few ions, and it will be information for you. Cool. Send me a reminder. I'm on that. Send it. You walk and run, and then you see if you have a really neat. Just always when you know you want to dramatically way. But he didn't probably ocean is good, doesn't mean it is incremental, so she's still a dramatic stuff. Then if you have issues, we can make connection between this and this.
Wait, so you think that they're just basing coproheme off of heme?
Potentials that were not extracted from each.
But still, I mean, I can still, if I can simulate it.
Just we don't even send it every time. Really have some sure challenges. Trying to make all the task and okay, what you pay. So I like remembers. Sure. Okay, thank you.
My turn?
Yes.
I'm just talking, okay, Adam, I'm gonna go. My turn. Okay. Thanks, Mikey. I was talking to the other undergrad and I'll CP. Cause he has a manuscript on the deposition, but, okay. So I made it so close, I put on the functional groups. But I don't know if it's rotated right, you know, if they're. Okay.
You can send him this one and he will run stuff there.
Okay, but also, so. I wanted to model the mu oxo compound, right, but also the dimerization. So I was asking how, if we know anything about the directions. There's a poster in our lab that he was reading on, and it's pi stacking. So it dimerizes. Would that be interesting at all to research?
So, you can just remove the central oxygen
Mhm.
and do 2 runs.
Okay.
Well, in this class, in this semester, we do some initial calculations. It's not complicated, but it takes some background if you want to take an active course. Part of this labs, of course, you can do it. You don't have to do it too much. So, use the backgrounds. So,
And would temperature dependence, pH dependence be?
it's all good, but
Okay.
let me tell something, and I will share my vision, which can be very, I just interviewed you today, so it's very research. Two constants. So I'm
Yeah.
this observations. Then we do potential as function of this distance across. No oxygen, there will be high barrier between and electronic excitations will be stage. But they physically you cannot mix, and if you have some it has a perfect relationship to extract the spectrum that they observe spectrum. Extraction will be very, very rough.
So we can do this with the whole spectrum.
Yes,
Is what you're saying.
yes.
Okay.
Now, if you do the same attention, this function, but electronic position across. With oxygen, then I anticipate that the barrier will be substantially lower. Let's see. By remove this. This one. This one. One can create charge transfer excitations, which will be very dark. Their strengths will be like orders of magnitude in the same frequency region. The spectrum will be substantially less intense. So this height of the barrier will immediately explain the diameter is dark. If it is what you see on experiment.
Yeah.
So it is what it's.
Okay.
And we can either model or provide didn't provide potential. It's a routine procedure. Sirens.
Yes.
You as an expert.
Yeah, but we've been doing it aerobically.
One for the excitation. Because we know the features towards excitation, if you Swiss church does.
Yeah, because it'll jump over
I
there.
think, and even those are churches transferred. It's a plus, 2 is plus. And if you break one bond and make a double bond, so you can efficiently let them to depart from each other in space. But then when you relax, so they will recombine and we can show as interacting for a distance and see that in ground excited state they if you excite they depart, if you let them connect, they combine.
Okay.
I need your input and your thoughts on these ideas. It depends. 20.
Okay. So these are the two different paths for the.
Ideal when the nature has everything, but we cannot do simulation with everything at the same time.
Okay,
And then in limited time, probably one can do all in one. If you try to do it, it will be like just a little too much.
okay. So what would this one, so this would give us,
It will explain the darkness of the first excited state of the time.
okay,
And this one will just prove or will illustrate that upon for excitation, temporization is loosened, it may break. I found a publication doing femtosecond experiment doing this hypothesis. I'm sure.
oh, okay. Okay, yeah.
And we make it so this that we may have
Yeah.
three of us, you, me, and more than 10. Sure.
Okay, and we have group meeting at 8 tomorrow, so I can ask it.
Opinion, the vision,
Yeah.
and I don't care about anything. It's just for you, project.
Yeah.
But Dr. Roger said you select whatever seems reasonable, and the constraint that it should be some simple model.
Yeah. Okay, and do you want, so I was thinking, does this seem too simple for a project or?
No.
No.
If you completely do it and explain it, it's exact.
Good, okay.
I think we are about in time, right? 5 minutes over. So any questions anyone wants to have more of the discussion for? So we are ready. Yes. So please send me reminders. It's my disease. I give more promises that I can fulfill, but I really appreciate reminders. Really, I need to reply and fulfill what I promise. If you don't hear from me immediately or unreasonable time, send them by your reply and arrange helpers to provide potentials or whatever. Maybe what I promised. I was openly doing it, but by talking to people, I may have already forgotten. So please give me a favor of announcing the adjourned. Like a mini, right? So we will see each other on this Friday, Monday, and then we have like very long weekend. Thanks again for votes in this exciting summit.
You said you wanted me to email Dr. Am I ready?
You CC to me. I already said it shows in the videos.
Yeah.
Yeah, so it's what? It's current. Right, and then there will be already. The great for the mothers.
And
my gosh, she's so crazy.
Guys, we have 20 minutes. Okay.
Are we doing, do we wanna, do we,
My car.
do we wanna-
20 minutes.
do we wanna go to, Sugi?
That deploy 2D or why not have to do that?
Rather
I don't care.
Is there a question?
Riley still might do that.
We don't have to do it in our office.
Adam's point to want to do his.
And the code is quite universal. You just need to change potential. You need to re-input, and then run the code. So, and all these things of converting matrices between dimensions are all there.
Okay.
You don't need to rewrite it. We basically, the projects here, if you want to present them for simplified, it's just rewriting the code with different potentials. It's not your task to modify the code. We just do exploration of more or less nature of objects.
No,
By
there's no point in putting this right
Is
potential.
dating anymore?
Right. You sense. I'm happy I don't have to think about what to do best. But yeah, in that case, maybe I'll email him this Friday or
Wait.
thereafter, we'll see. Anyways, have a good rest of your,
Yeah, it's a
See you Friday.